Hello friends, welcome to your channel Phy-LAB. Learn, analyze and build physics concept. Channel dedicated for understanding physics at +2 level. Thanks to all of you for browsing into this channel. Kindly subscribe to this channel if you haven't done up till now. And don't forget to hit the bell icon to get notified whenever I post a new video or solution from Newton Physics textbooks.
Friends, today we are discussing about Wheatstone Bridge combination, which happens to be a combination of circuit elements connected across the arms of a quadrilateral and across any one diagonal of that particular quadrilateral. Over here, if you can see, there is a quadrilateral A, B, C, D, and across the arms, if you look at the arm here, at the arm AB, some circuit element P may be connected, another arm Q circuit element may be connected, and so on. Another this arm S, over this arm R, and across the diagonal. And the net resistance or net capacitance or the net circuit component is required to be found across the other diagonal, which happens to be AC. Now, if you get such type of a combination, then such combination of or such arrangement of the circuit elements is often referred as Wheatstone Bridge combination. Now, the most important thing about the Wheatstone Bridge combination is in this arrangement, none of the circuit elements are either connected in series or connected in parallel. That is one thing that you should keep into mind. But there is a special case that happens, and which brings this particular arrangement into a simpler formation, and that happens when there is no current that flows across this particular diagonal, that is the diagonal BD. Then this circuit is easily solvable. Otherwise, what you require Kirchhoff's law to solve such type of circuit combination, and you can refer to my video given in the description link for how to solve an unbalanced Wheatstone bridge combination. Presently, we are going to discuss about a balanced Wheatstone bridge. Now, this balanced Wheatstone bridge is going to become easily solvable when the Wheatstone bridge is balanced. Now, when I say Wheatstone is balanced, what does it mean? That there is no current going to flow across this particular diagonal, and that happens whenever the ratio of the circuit elements are in proportion. That means the ratio of P upon Q is in proportion to R upon S, or alternatively P upon R is equals to Q upon S. Then the bridge is balanced. This particular circuit element, diagonal element, is no longer in use, so you can consider it to be open. And then once you consider it to be open, then what happens? P and Q comes in series combination, R and S comes in series combination, and the series combination are connected across parallel to each other. So PQ and RS in series, and they are in parallel to each other. Now the proof of the same. So if there is no current flows through the galvanometer, that means this diagonal branch, then we say the bridge is under a balanced condition. Now, in order to happen this, what is required? That the point B and node D, this node B and this node D, must be at equal potential. So I can say that VB must be equals to VD. Now, in this particular situation, only the current can't flow in this particular diagonal branch. Now, if this happens, then remember this point A is basically the common point. So VAB and VAB will be equal. Similarly, C is the common point, then I can say VBC and VDC are also going to be equal. Now, if you are sending some current through the node A, and let me say the current that I am sending through the node A happens to be I, and this current I that flows from this node gets divided into two branches, I1 in the above and I2 in the below. So I1 goes from the upper branch, I2 from the below part, and there is no current that is going to flow in this branch, so bringing P and Q in series and bringing R and S in series, and the two in parallel to each other. So in that situation, the potential drop that takes place across VAB will be equals to I1 times P, isn't it? The potential drop that takes place in this particular branch will be I1 times P. Remember that formula of Ohm's law, V is equals to IR. And then the potential drop across VAD branch will be equal to I2R. Current flowing in this branch is I2, and the resistance of this branch happens to be R, I2R. Similarly, in this case, VBC will be I1 times Q and VDC will be I2S. And dividing then these two equations, I1P is equals to I2R, this is equation number 1, and I1Q and I2S will be my equation 2, and just dividing these two equations, I1 goes off, I2 goes off, and giving me the balanced condition, which happens to be P upon Q equals to R upon S. Now you have got different ways of representing Wheatstone bridge combination. I can show you some of the very commonly used ways. This is also a Wheatstone bridge combination. This is also a Wheatstone bridge combination. This is also a Wheatstone bridge combination. This one is also a Wheatstone. In fact, these two are very similar combination. This is the diagonal one, these two. Then this one happens to be this one. So there are the certain ways in which the teacher can put up the question in front of you. So you can practice them, and I will come out with a number of solution of different types of Wheatstone bridge combinations in future. Thank you.
Hoping guys you all must have enjoyed learning with this video. Please share this video with your friends and classmates and add in your comments which topics you want me to do for you or any specific numerical problems you want me to solve for you. Thank you and enjoy learning.